Good afternoon. Today's topic is transitive closure of a graph. So, the transitive closure of a given graph G is G asterisk. Here, we are talking about directed graph. Such that the vertices of G asterisk remains the same as the vertices of G. Suppose this is the vertices of G and this is also the vertices of G asterisk. So vertices are the same A, B, C. Then it has the same vertex A, B, C. But and the uh, from one vertex to another there is a path in transitive closure whenever there is a path from A to B. So suppose I am talking about the definition. The transitive closure of a directed graph G is itself a directed graph G epsilon such that the vertices of G epsilon are the same as vertices of G. And G epsilon has an H U to V whenever there is a directed path from U to V in origin given graph G. Let's see example. We are given the graph 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1. This graph is given now. We can see that it has n cross n matrix. So we can assume that this is a adjacency matrix representation because adjacency matrix has n by n representation. How to draw this graph? Let's make it easier. 0, 1, 2, 3. 0, 1, 2, 3. This is the 0, 1, 2, 3. 0, 1, 2, 3. These are the vertices. So from 0 there is the path 0 to 1. There is a path 0 to 2, 1 to 2, 1 to 2, 2 to 0, 2 to 3. 3 has no outgoing edge. This is the graph given. How to draw is transitive closure. Suppose we have no time for algorithm, just we are given the picture. So how to find it? The easiest way. Just draw the vertices as given. Just no change. 0 to 1 there is a path. Yes. 0 to 2. Yes. 0 to 2. 0 to 3. Is there any path? Can we reach 3 from 0? 0 to 2. 2 to 3. Yes. 0 to 2. 2 to 3. 0 to 3. There is a path. So 0 to all checked. 1. Can we reach 0 from 1? 1 to 2. 1 to 2. Then 2 to 0. 1 to 2, 2 to 0. So there is a path. 1 to 2, yes. 1 to 3, 1 to 2, then here, yes. 1 to 3, okay. Let's check 2. 2 to 0, yes. 2 1, and 2, then 0, then 1. 2 0 1, yes. 2 2 3, yes. Any path from 3 to 0? No, it's a directed path, we cannot reverse, so 3 has no outgoing edge. So this is our transitive graph or directed transitive closure of a directed graph G, and we use an asterisk sign to mean it is a transitive closure. We also see use transitive closure in regular expression. In this case, we use Klein's algorithm. Cross-check this word. Okay, Klein's algorithm, I'm not sure of is letter arrangement. Okay, just cross-check. So what is the output of this transitive closure? This is a graphical representation. 0 1 2 3. We see that we can reach everyone to everyone. Okay. But 3 has no one. So how to, again we make a matrix. 0 1 2 3, 0 1 2 3. So if there is a directed path from 0 to 0, we write 1. 0 to 1, then 1. We can see that except she has no outgoing edge to any other vertex. So from 3 we can travel nowhere. So write 0. And we see that we can travel everyone. Now we have from 0 to 0 we can travel because we are already in 0. So we make it 1. Okay. And this is our output. This star. We have asterisk. Okay. This is the answer. So we have seen so far how to solve transitive closure problem without using any algorithm or program. Now let's see how to solve it using a Python program. We use Floyd-Warshall algorithm for finding transitive closure of a graph. So this is a graph given. Let's write it. A 2D array. So how this works? I think it's fairly simple. We don't need any pseudo code. We just use the code. Define transitive closure. We input the graph in the parameter as L equal length of graph. Okay, how many vertex? We don't want to modify the graph, so we make a shallow copy of the graph. So we use x equal graph dot copy. This is a shallow copy. So original graph will not be modified. Now let's see. We pass 3 loops. Okay. For k in range L. For inside it I in range L. For j in range L. Now why there is a such nested loop? Let's see. X is the output. Okay, we modify the copy graph and return it as output. Now if there is a directly path between I to j, between I to j, this is I, suppose this is j, there is a path? No. But if there is a directly path, one means there is a path. So if there is a path between I to j, then we can include 1 in x. So if also if I equal j, that means from A, B, C, D, same vertex to same vertex, there is a path. So if I equal j means this is a same vertex. So A to A, there is always a path. If I equal j, x I j equal 1. Okay. Now and if just you will find this algorithm in websites. It's a very common algorithm. So let's write it again. I equal j x I j equal 1. Okay. If L if E L I F, suppose A B C, there is no from A, there is no direct path to C, but from A we can reach B, from B we can reach C. So we can say A to C is valid in the transitive closure. So if x I to k equal 1 and x k to j equal 1, then we had this part in transitive closure, x I to j equal 1. So that is intermediate is k, I, j. So I to k equal 1, k to j equal 1. So I to j equal 1. Test easy. And because there is a 3 nested loop using V cube, we use every possible permutation. So eventually we get the transitive closure for loop I, j, k. Now what is the output? We return print x. Okay. Done. Now this was our transitive closure function. Finally we use transitive closure graph. So we call the function and the function prints x. What is x? We have already seen the output. What is the complexity? We use k for L times, I for L times, j for L times. What is L? L is the number of vertex V. So what is the time complexity? Big of V cube. What is the space complexity? Initially, actually, if we use the original graph, we modify the original graph, there is no space complexity equal 1. But we don't want to modify the original graph, then the space complexity of big of V square, because we use a copy graph. Hence, that's all for the transitive closures.